Hello everyone, and welcome back to C++ Real-Time Audio Programming with Bela. I'm Andrew McPherson, and in this series of lectures, I'm taking you through the basic topics of creating synthesizers and audio effects. And for each music and audio topic, these are associated with one or more programming topics in the C++ language. For today, we'll be looking at classes and objects in C++, and we'll be seeing this in the context of building up an additive synthesizer of wavetable oscillators. In this lecture, you'll learn about the basics of working with classes in C++, and we'll also see more about working with arrays using the C++ vector object. I'll also introduce the concept of additive synthesis and why it might be useful. And as a bonus, we'll also look at why so many simple digital oscillators just sound bad, and what it is that you can do about it. By the time you finish this lecture, you will have made an additive synthesizer which can generate complex waveforms out of simpler harmonic components. As always, there are companion materials, including code examples for this lecture, on the GitHub link at the bottom of the screen. To follow along with the code examples, you'll need a Bela starter kit or a Bela mini starter kit. And starting in the next lecture, you'll also need a few basic electronic components, including a breadboard, some potentiometers, some resistors, and jumper wires. More details on those components can be found on the companion materials for Lecture 0. A reminder for those just joining us that you will need the latest version of the Bela core software to run the examples for this lecture. If you haven't updated your board recently, please do so from learn.bela.io/update. Let's pick up from where we left off in the previous lecture. We saw that a common technique on analog synths to produce a richer sound was to have multiple oscillators tuned to nearly the same frequency, but not exactly the same frequency. This slight detuning results in a beating or chorusing effect that makes the oscillator sound richer. In the last lecture, we took a wavetable example and implemented two wavetable oscillators at the same time. We had two controls, one for setting the center frequency of both the oscillators and one that changed the detuning ratio between the two. And we used these formulas to calculate the frequency of each individual oscillator. In the process of converting our code from one wavetable oscillator to two, we had to figure out which bits of code needed to be duplicated and which ones did not. So let's review some basic questions. How many copies did we need of the wavetable itself, that is to say the buffer and the samples within it? For two oscillators, we saw that we actually still only needed one wavetable, and we could just look into it at two different places. So how many copies of the read pointer did we need to look inside of the wavetable? Well, each oscillator needed its own read pointer, so we needed two read pointers to implement two oscillators. How many sliders did we need to control this? Well, we needed three sliders, one for the amplitude, one for the frequency, and one for the detuning ratio. And then how did we calculate the frequencies? We saw this on the previous slide. We implemented those equations, which in code would look something like this. And then maybe one of the trickier bits was, which code in render did we need to duplicate, and how could we duplicate it? First, did we need two copies of the outer for loop, which stepped through each of the audio frames? The answer to this is no. We still needed to only go through the audio frames once. Did we need to duplicate the code which calculated the output value based on the integer and fractional indexes? In this case, yes, we did, because we had two different read pointers and the code needed to be repeated for each of the read pointers. Did we need to duplicate the bit updating the read pointer? Again, yes, with two different read pointers, this bit of code needed to be run twice. And how about the for loop, which actually wrote the output to both of the audio channels? In this case, the answer was no. Our first attempt at making two oscillators involved copying and pasting a big block of code. We saw that this was rather bad because it led to a significant potential for bugs either now or later on. We ended up with a solution involving multiple nested for loops inside of render, but we still needed a number of variables at the top of the file. The question is there a cleaner way of dealing with multiple oscillators at the same time? The answer is yes. Potentially the cleanest way to deal with multiple oscillators in C++ is to encapsulate both the variables and the code for implementing an oscillator into a class, which lets us create multiple objects, each of which represents a complete oscillator. Let's talk more about what we mean by classes. But first, let's step back a couple lectures and look at a C programming concept called a struct. Struct, of course, stands for structure, and it is essentially just a container which holds particular named data inside of it. The place where we saw a struct in action was this thing called Bela context, which passed in all of the state to our render function. And we saw that Bela context contained within it a number of different fields holding things like input and output samples, numbers of channels, sample rates, etc. And we saw that this Bela context struct was passed into the render function as a pointer, which meant that the struct was located somewhere in memory and that the pointer told us where to go find it. We also saw how to access individual elements within the struct, which involved this little arrow operator. So if we wanted to access the field called audio sample rate, we could do that through context arrow audio sample rate. If we were working directly with a struct rather than on a pointer to a struct, we would use the dot operator rather than the arrow. I bring this up because working with classes in C++ is essentially just an extension of working with structs in C. When we talk of defining a class, we're really talking about defining a container with specific named elements inside of it. In the ensuing examples, we're going to make a class called wavetable, which implements a wavetable oscillator. You can find in the companion materials a project called wavetable-class, and you can follow along with this there. The example that we'll consider in these slides is slightly simplified from the code, but we'll look at the code when we're done. Like a struct in C, a C++ class can hold variables of various different names and types. And the class effectively functions as a data type, which means that we can create objects of this type. So here we can create an object of type wavetable, and each wavetable object is going to have inside of it its own copies of each of these variables: sample rate, frequency, phase, etc. Declaring the object works like declaring any other variable. So instead of being a float, in this case, W is of type wavetable. And then if we wanted to access the variable called frequency within W, we can do that with w.frequency. And just to emphasize, if we had 3 different wavetable objects, each one could have its own frequency. What makes a C++ class different than a struct in C is that it can also hold functions. When we define a function inside of a class, it's known as a method. What makes a method special is that it has automatic access to all the variables declared inside the class, and calling the method for one particular object is going to access the values of the variables associated with that particular object. So here, in this example, we have a method called process inside of our wavetable class. If we declare a wavetable object called W, we can run the method by calling w.process. And the method called process will have automatic access to sample rate, frequency, phase, and any other variables that were declared inside the class. And again, if we had multiple objects of this class, then each object would be working with its own copy of those variables. Now you can see in this example that we have declared a method called process. It takes no arguments and it returns a float, but we don't see here where process is actually implemented. How can we do this? There's a couple different options. One possibility is to implement the contents of the method within the class definition itself. We can see that in the code example here. And we can see that the process method is indeed using the variables declared inside the class, even though those variables are not declared within the method itself. This is effectively like using global variables, but with each copy of the object having its own copy of them. You can see at the end of this method that there is a return statement, like there would be returning from a function, and this specifies what value should be returned to whoever called the method. There's also a way of implementing a method outside the definition of the class. In this case, we only need to declare the prototype within the class definition. That is basically the name and arguments of the method, but just with a semicolon at the end. Then what we do is somewhere else outside the class definition, we can declare it using this : operator. So you see in this example, we can declare float wavetable : process, and then we have our implementation. This basically tells the compiler that this code belongs as the implementation of the method declared in the class. A very common convention, which you'll see in the companion materials for these lectures, is to have the class definition in a header file ending in .h, and then to have the implementation inside of a .cpp file. Let's look at a few other features of C++ classes. Classes will typically have a constructor. A constructor is a special method which is always run automatically when the object is created. You never have to call the constructor for yourself. We always know which method is the constructor because it has exactly the same name as the class itself. The constructor is where you should do any initialization that you need for the contents of this object. It's also possible to have multiple constructors for a class which take different arguments. Which of these constructors runs depends on how your object was created. In this example here, you can see that W1 was declared without any arguments, which will run the default constructor, whereas W2 was declared with one argument, which is going to run the second of these constructors. The counterpart to the constructor is the destructor. The destructor is also run automatically, in this case when the object is destroyed. For example, at the end of a function where the object was declared, or, in the case of dynamically allocated objects, when the delete statement is called. The purpose of the destructor is to do any necessary cleanup. Oftentimes this will be handled automatically for you and you don't need anything in the destructor, but for instance, if you were doing something like dynamic memory allocation, you'd need to free the memory here. A few more points of syntax before we specifically get into working with audio. You will see within class definitions these keywords called public and private, followed by colons. Any variables or methods which follow the public statement are accessible to any outside caller, whereas any variables and methods within a private statement can only be accessed from methods of that class itself. There is also a third keyword called protected, which works like private except that subclasses which inherit from this class can also access those elements. We won't talk about class inheritance today, but the broader point here is that it can be good coding practice to shield the internal implementation of your object from the outside world and only expose those methods or variables that you know that outside callers will need to use. Along those lines, a convention you'll commonly see in C++ is to declare all of the class variables to be private. What that means is that you can never directly access a variable from outside the class. So in this example, the variable frequency is a private variable, but we have methods for getting and setting the frequency which are accessible to the outside world. A reason that you might want to do this, for example, is if you wanted to limit the valid ranges of frequencies. You could have your setFrequency method check whether its argument was in a valid range. We will also commonly see naming conventions for your instance variables, which are those declared inside the class itself rather than within a method. In this particular naming convention, I've added an underscore to the end of each of the variables that are declared within the class, so that when I'm working within a particular method, I can easily identify which variables were declared in that method versus in the class itself. This is a very similar idea to having a naming convention separating global variables from local ones. Here then is an approach to how we might use classes in our Bela projects. To begin with, we'll make a file called classname.h within our project. This is what's called a header file. Then we're going to make another file called classname.cpp. And inside of both classname.cpp and render.cpp, we're going to have this statement, #include classname.h. What that says is basically to literally include all of the text within classname.h inside of both of these CPP files. That lets us have the definition of our class available to us in each of the C++ files we're working with. The next things then that we need to do is to create objects of this class. In the examples we'll see today, these objects will be declared as global variables, though there's no reason that that needs to be the case in general in C++. To reiterate, we are not directly calling the constructor of the object. That will run automatically when the object is declared, and the same with the destructor. Finally then, to use the objects we just declared, we just access the methods, or possibly the variables, within our Bela setup and render functions. One particular place we'll make use of classes in this lecture series is defining basic signal processing units that we might want to reuse over and over again. And there's a particular convention that you'll frequently see within a real-time audio context. The convention includes a method which is designed to be called once per audio frame. You're going to pass in as parameters any input signals that you want to process, and the return value will be its output signal. Here we call that method process, and it's designed to calculate one frame of the audio output and return it back to the caller. And at the same time, the method will also update the internal state within the object to save it for the next frame. For example, if your object declares an oscillator, then this method might return the next sample of the oscillator, but also update the phase so that the next time you call process, the oscillator picks up from where you left off. Beyond the process method, it's also useful to have other methods which you might use to update the state or the parameters of this object. For example, in the case of an oscillator, you might have a method to call to change its frequency, and it might be that you don't need to change the frequency of the oscillator as often as you need to calculate the output, and that's why you would declare this as a separate method rather than making it part of the process method. A Bela-specific consideration is whether our class should know about the Bela context or not. And my recommendation is that in most cases it shouldn't. Because a lot of the classes that we'll implement will be for generic signal processing applications, there's no particular reason to tie it to the implementation details of Bela. Instead, the idea is to encapsulate everything you need for the signal processing inside of that class in a platform-independent way, and then leave all of the Bela-specific stuff to the render function. There are some exceptions to this. For example, if you're making a class which works very specifically with hardware communication on Bela, then you might as well know about the Bela context if it's convenient to do so. Though one important caveat is that you can only use the Bela context inside the render function or any function called from render. There's no way to cache the Bela context, for example, to be used in a different thread, because the data is refreshed every new call to render. Now that we've seen the outlines, let's have a look through the wavetable class example. Remember that to put this project on your board, you download the zip file from GitHub, you drag it onto the browser, and it should prompt you to create a new project. And here we are with the wavetable class example. You can see here that it's using the GUI and also using the browser-based oscilloscope, so we can open both of those things. Here's the GUI and here's the scope in the toolbar. And this example is also including the file wavetable.h. As we talked about, wavetable.h contains the declaration of the wavetable class. So let's first look at that. Here's the declaration of the wavetable class. You can see it's class wavetable and then curly braces. All of the public and the private elements of the class are declared in here. Close curly brace and notice that we need a semicolon at the end. That's different than declaring a function and can be a bit confusing. We can see that this class also relies on another object which is called vector. We'll talk about that more in a little bit, but we see that we have a hash include statement here inside of wavetable.h to give us the necessary declaration of the vector object. Looking inside the class, we can see that we have constructors, two different constructors in fact. The first one takes no arguments, the second one takes several arguments. One is the sample rate, the next is the contents of the wavetable that we want to use for our oscillator. The final argument is whether or not the oscillator should use linear interpolation on the wavetable. Notice also a convention here where we have a parameter and then we have equals true at the end. This is the parameter taking a default value. What that means is that we can actually declare a wavetable not with 3 arguments, but with only 2, and if we don't specify use interpolation, the default value is going to be true. Here we see some other methods. We have a setup method. As you might imagine, this is something to be called once at the beginning of the program, and then we have our parameter getting and setting methods here, which are working on a variable called frequency, which is itself private. We have our process method, which is going to be called once per audio frame within the render function. And then finally, we have the destructor. Notice that the destructor doesn't actually do anything, which is why we just have these blank curly braces here. Down at the bottom, we have a series of instance variables. By convention, these have the underscore after their name just to remind us that they're declared inside the class and not within a particular method. The vector is going to actually hold our wavetable itself. More on that in a moment. And then these are some other variables that we're going to use to implement the oscillator. Now if we go over to wavetable.cpp, we can see the implementation of the wavetable oscillator. First of all, notice that it is also including wavetable.h. We need to do that so that we have the declaration of the class available for us. Here's the implementation of the constructor that took 3 arguments. It's just passing those arguments on to the setup method, which is in turn declared here. The setup method will do various useful initialization. For example, it's going to take the sample rate of the system and it's going to use that to compute something called inverse sample rate. The reason that we do this is that it's usually faster on most platforms to multiply variables than to divide them. And because our phase computation relies on dividing the sample rate, if we pre-compute its inverse, we can just multiply by that then later on. Let's have a look specifically at process then. The code for this should be familiar from previous lectures, especially lecture 2, so I'm not going to talk about this in detail. Instead, just to say that we have a basic check to make sure that we do have a valid table before we go any further. We are working with incrementing our phase here, and then this code implements our linear interpolation if indeed it is enabled. If it's not enabled, we just look at the integer right below wherever the read pointer is, and then finally we have our return statement which returns the output value which is looked up from our wavetable. So that's our declaration of the wavetable class. Now we can go back over to render. Here we can see that we have declared a single wavetable object. The wavetable object name is gOscillator. Its type is wavetable, which of course is the name of our class. And then if we look inside the setup function, we can see that we're calling the setup method of gOscillator. We're passing into it 2 arguments. The first is the sample rate of the system gotten from the Bela context, and the second of these is the wavetable that we have computed up here. More on this momentarily. Notice that there are only 2 arguments going into setup. The third argument doesn't exist here, and so it's going to take its default value that we saw, which was true. We're doing some other setup on the GUI and on the oscilloscope, which we're not going to talk about here, but then if we go into our render function, we can see that we're using gOscillator. Here we're calling the set frequency method of g-oscillator to set the frequency of our oscillator, and then once per audio frame within this for loop we are calling the process method. Once again, the process method is going to return the next sample of the oscillator and update the phase for the next time round. We can run this example now. We can open our GUI with this button here, and it'll load up a GUI and show us that we have two controls, one for frequency as a MIDI note and the other as amplitude in decibels. And these controls build on what we saw in the previous lecture. So we can change the pitch up and down, and we can change the amplitude. We can also go back over here and we can open the Bela oscilloscope, like so. And here we see our sine wave. The last thing to look at before we move on is how the wavetable was computed. Notice that we have declared inside of setup this variable called wavetable, which is of type std::, vector, and then in angle braces float. This is essentially an array of floats, and the vector object in C++ is a more full-featured version of the array concept compared to just declaring a basic array with square brackets. What we then do is we resize the vector to have the right number of elements in it, in this case 512, and then we write a for loop which goes from 0 up through 511 and stores the computations of the sine wave inside the wavetable. More details on this can be found in Lecture 2. So far, that's just a way of taking the oscillators we've already made and writing them in a different format. But as we'll see, making classes like that makes it very convenient to make large numbers of oscillators. And this is useful for a concept called additive synthesis. Additive synthesis is essentially just a method of building up complex sounds out of simpler subcomponents, most frequently sinusoids. And Fourier theory tells us that every periodic signal can be represented as a sum of harmonically related sinusoids. What that means is that we can basically take sine and cosine waves, which are related as integer multiples of some fundamental frequency, and we can add them together with different amplitudes to reconstruct any possible periodic signal. This in turn is a special case of the Fourier transform, which shows how we can represent any signal at all as a sum of sinusoids. Let's look at an example that we saw in a previous lecture. We had defined a signal called W of phi, where phi is the phase, and it was the sum of 4 different sinusoids, 1, 2, 3, and 4. And these sum together to form the black signal that we see here. So to turn this around, what Fourier theory tells us is that this black signal can always be decomposed back into these original 4 sinusoids. The idea with additive synthesis often is to control the timbre of a sound by altering its spectrum. When we talk about the spectrum of a sound, we're essentially talking about the amplitude of different frequency components of that sound. Now, a caveat is that timbre is an enormously complex topic, one that's still the subject of considerable research, and it's much more complex than just the amplitudes of particular harmonically related waveforms. Nonetheless, this is still a good starting point. Let's consider some common oscillator wave shapes and how these decompose into sinusoids. First of all, our venerable sine wave can be trivially decomposed into a single frequency component, literally the sine at its fundamental frequency. A triangle wave, however, is composed of infinitely many harmonically related sinusoids. You can see here that as the frequency of each component goes up, its amplitude quite rapidly drops. A square wave is also composed of infinitely many sinusoidal components added together. In this case, the components are the same, which is to say, the odd-numbered harmonics only. Why are there only odd-numbered components for the triangle wave and the square wave? Well, the reason has to do with the symmetry of the waveform itself. Notice that the waveform has odd symmetry, which is to say if you look at the first half of the waveform, it is essentially the inverse of the second half of the waveform. Any waveform with this property of odd symmetry is going to involve only odd-numbered harmonics. An example of a common waveform that doesn't have odd symmetry is the sawtooth. In this case, the sawtooth involves adding together every frequency component with an amplitude equal to 1 divided by the harmonic number. So, for example, the second harmonic has an amplitude of 1/2, the third harmonic has an amplitude of 1/3, and so forth. I want to reiterate that the harmonic series for these waveforms are infinite. They do not stop at any particular frequency, even though they gradually diminish in amplitude towards 0. The question is why this might be a problem in the digital domain. I'm going to leave this as an open question for the moment, because what I'd like you to do is to take the wavetable-class example that we just ran and change the calculation in setup so that instead of generating a sine wave in its wavetable, it generates a square wave. The way that you can do this is to have the first half of the samples have a value of 1.0 and the second half of the samples have a value of -1.0. You might even find it helpful to turn off linear interpolation for this test. Once you've made that change, run the example and open the oscilloscope. First, you should be able to see the square wave in the oscilloscope, and once you've done that, change the scope from time domain to FFT mode. This is going to plot the spectrum of the signal. Once you've done that, then click the button that says Toggle Controls, and I want you to change the scope to have 2048 points and decibel scale on the y-axis, which is going to make it easier to see some of the higher frequency components. And I want you to notice what you see there as you change the fundamental frequency. Pause the video here and we'll look at it together in a moment. Here we are with the wavetable changed from a sine wave to a square wave, and notice that I have also turned off linear interpolation on the oscillator. I can run this, and we can see on the right-hand side of the screen what turns up on the oscilloscope. There we see our square wave. We can go over here to the GUI, and we should be able to change the frequency and the amplitude. Now let's turn the scope to FFT mode. Go over here, we'll change from time domain to FFT. To begin with, we can see the gradually diminishing harmonic components of the square wave, each of them spaced linearly apart in frequency, and they get smaller up until this point, and then something funny happens. Instead of stopping, they reflect back downward, and we see all of these extra spurious frequency components which are nestled in between the harmonics of the square wave. What is going on here? First of all, we can move around the frequency of the square wave, and we can see that these components also move in a slightly funny way. So you can see that some of the frequencies, they're more noticeable than others. Strange. This helps answer a very important question about why digital oscillators often sound so bad. As we saw, the harmonic series for these waveforms are often infinite, gradually diminishing in amplitude but never reaching zero. The problem that we have here is that digital signals are limited to no more than half the sample rate, which is known as the Nyquist rate. Any frequency components above the Nyquist rate are going to be aliased, which basically means that they're going to be reflected downward back into the lower frequencies, oftentimes in a very inharmonic way. So in this particular example, suppose that our Nyquist frequency was here, right above 9F. What will happen is that these three higher frequency components will be reflected back into the lower frequency region, and there they are no longer harmonic with the original fundamental frequency. And this aliasing is often responsible for the poor sound of digitally generated squares and sawtooths. Well, what could we do about this? Additive synthesis offers a potential solution. Using our wavetable class, we could build up a square wave for ourselves, one harmonic at a time, being sure to never have any harmonics that go above the Nyquist rate. What this will take in practice is to have one wavetable object for each of the sinusoidal harmonics of the square. Obviously, we can't have an infinite number of these, but as we saw in the oscilloscope, we don't need more than a few dozen to reach the Nyquist frequency. What we're going to need to do is to make an array of wavetable objects, and this has been started for you in the project called Additive Synth, though the project is unfinished because it's left as an exercise here. What we're going to do is use the C++ vector object to make an array of wavetable oscillators. So notice here that we have standard : vector, and then in angle braces, wavetable. This declares the type of the vector. Just like we could have a vector of floats, we can very well have a vector of wavetables, wavetable being the class that we defined. Then inside the setup function, we're creating each of the oscillators, and we're calling this method of vector called pushback. What this means is append this particular object to the end of the vector, making the vector one element longer. This is not something that you would be able to do easily in a standard C array, but it's very convenient in C++. There's a link to more information about the C++ vector class on the companion materials. The other feature of our additive synthesizer is going to be to have controls which let us manually adjust the amplitude of each individual harmonic component. We'll start out by implementing the amplitudes of a square wave, but then you can adjust it yourself in the GUI. So you'll find inside the setup function the following for loop. It starts out with some C++ string formatting stuff that I'm not going to get into here, But the important part is that for each iteration of the for loop, we are adding a slider to the GUI, giving it a default value and a range of -60 to 0 dB. And then finally, we have the calculation of the amplitude in decibels for each harmonic of the square wave. This looks a little bit complex because we have to have all the even harmonics be set to a value of 0 and all the odd harmonics set to a decibel value. So here we're using the formula from the previous lecture converting linear amplitude into decibels. Notice that -60 dB is the lowest value that we can store here. Later on in our render code, we should set it so that a value of -60 dB is just turned into an amplitude of 0 or muted. The rest of it then is left to you. Put the additive synth example on your board, and you should be able to see that the GUI runs, but you won't hear any sound because you need to implement the code inside of render. The code inside of render is going to need to do a few things. It's going to need to set the frequency of each of the oscillator objects to be an integer multiple of the fundamental frequency. You're also going to need to get the amplitudes from each one of the sliders that was created there, and then you're going to need to convert that amplitude from decibels into linear amplitude. I suggest that if you get a value of -60 dB, you treat that effectively as mute or off and just set the amplitude to 0. Otherwise, perform the decibel to linear calculation. Store these values inside the array that's already declared for you called gamplitudes because you'll find that easier to work with afterwards. Then finally, you'll need to use the process method of the wavetable oscillator to get the output of each one of the oscillators and add them together scaled by the appropriate amplitudes. Once you do that, you should be able to run the project, and I suggest that you bring up the GUI and the scope side by side to see how adjusting the parameters of the additive synth affects both the waveform and the spectrum of the resulting signal. Pause the video here. We'll look at some of the key bits of code first. This code goes at the top of your render function before the main for loop going through the audio frames. This for loop counts through the total number of oscillators. Notice that the C++ vector class provides a method called size that we can use to get the number of elements of the array. Inside this for loop, we're setting the frequency of each oscillator to the fundamental frequency times index I plus 1. The reason for this is that our array indices start from 0, but our harmonic frequencies start from a multiple of 1. After that then, we are getting the amplitude from each of the individual sliders that we created. Notice here that we're accessing slider index 2 plus I. That's because sliders 0 and 1 are the master frequency and master amplitude respectively. And then, finally, we are converting the decibel value to a linear amplitude, unless we get a value of -60. If that's the case, then we're just going to set that amplitude equal to 0 so we can mute it. Now this code, again, goes at the beginning of the render function. It does not need to be inside of the main for loop. The reason for that is that we don't expect the slider values to change within the call to render, and we talked about that in the previous lecture. Once we do get into the main for loop, then we have a different block of code that needs to run. And here, you can see that we have a for loop that also counts through the total number of oscillators, and it calls the process method on each one of the oscillators in the array. It multiplies that output by the amplitude for that oscillator and mixes it into the variable called out. Let's see this in action. Okay, so here we are in the additive synth example. We can adjust the frequency of the square wave. We can adjust the amplitude. And now let's look at how the square wave is composed of individual sinusoidal components. And now we're back to a sine wave. And now we can build up a different waveform. So that's a brief tour of additive synthesis. However, we still have a problem. Let's build up a waveform with all the harmonic components set to the highest amplitude. And now let's adjust its frequency. So far so good, but something strange starts to happen. We can see some odd things on the scope, and the higher frequencies start to sound very strange indeed. So we have a problem. Even with a fixed finite number of harmonics, we might still have aliasing. Therefore, the last task of this lecture is to implement a check of whether the frequency is higher than the Nyquist rate. If it is, then you should mute that particular oscillator to avoid aliasing. Pause the video here and try that. Here we have one additional change in the render function. We're checking whether the frequency of this particular component is greater than the Nyquist rate, and if it is, we set the amplitude equal to 0. Otherwise, we calculate its amplitude as normal. So we can run this, and we can go to the GUI to adjust the frequency. And now what happens? Much better. Wrapping up, we saw a few things in this lecture. First of all, we saw a basic introduction to C++ classes, and this was a useful way to encapsulate code so that we didn't have to duplicate it to make multiple copies of a particular synth unit. Now, of course, there's a lot more to say about C++ classes, and you can find some tutorials on the companion materials. We also saw in this lecture that additive synthesis is a potentially useful way of building up more complex waveforms, and that if we do it right, we can also do it in a way that avoids aliasing. This can be one approach to creating a better sounding square or sawtooth wave digitally. It is not necessarily the most efficient way of generating band-limited waveforms. In fact, there's been a fair bit of research over the past 20 to 30 years about how to generate band-limited waveforms digitally. I'll put some links to that in the companion materials. So thanks very much for following along with this lecture. As always, please click subscribe if you want to be notified of the new lectures as they become available, or follow us on social media at Bela Platform, or drop by any of our other online resources. See you the next time.